Now let's discuss the third partial exam. First one, we have three functions. Fx is the cube root of x. So don't forget this 3. G of x is 2x minus 1. H of x is x cubed. Then we're going to find the value of two expressions. First one is f compose g evaluated at 14. Alright, then by the definition it is f of g of 14. G of 14 is f of 2 times 14, 28 minus 1. So it's f of 27. So fx is cube root of x, so it's a cube root of 27. 27 is a 3 cubed, so cube root cancelled with a 3 cubed, so you get number 3. B, we're looking for h compose g compose f of 8. Right, it's a composite function of 3 functions, so it's h of g of f of 8. Okay, so you're going to evaluate f at 8. F of 8 is cube root of 8. Cube root of 8 is 2. Cube root of 8 is equal to 2. And then g of 2. G of 2 is 2 times 2 is 4. 4 minus 1 is 3. So g of 2 is 3. H of 3 is 3 cubed. 3 cubed is 27. So the answer is 27. So you have 3 and 27 for two expressions. Okay. All right. So second problem, we have again two functions. Fx as x plus 1 over x plus 2. G of x as x over x minus 1. We're looking for the composite function and the domain. So A, f compose g of x. F compose g, it is f of x over x minus 1. So in the expression of f function, whenever you see x, you're going to write x over x minus 1. So the numerator x becomes x over x minus 1 and plus 1. This is plus 1. Over the denominator x is x over x minus 1 and then plus 2. And to simplify this complex expression, we're going to multiply top and bottom by x minus 1. Remember, whenever you multiply top and bottom by a number, that number cannot be 0. So here, x minus 1 cannot be 0. This will give you a point outside of our domain. Remember that. So if you cancel them, so x minus 1 cancel with x minus 1, you have x. 1 times x minus 1 is x minus 1. Here, you cancel x minus 1, you get x. Then 2 times x minus 1 is 2 times x minus 1, exactly. So if you simplify it, it's 2x minus 1 and 3x minus 2. In the 3x minus 2, the denominator cannot be 0. Right? So combine these two things. The domain is the set of all real numbers. X is not equal to 1 and x is not equal to 2/3. 2/3 comes from here. X not equal to 1 comes from here. All right? So you have to give me the domain. You have to give me the domain. Second one, you see, it's a g compose f of x. So it's a g of fx is x plus 1 over x plus 2. So you have x, you're going to write x plus 1 over x plus 2. So x plus 1 over x plus 2. This is numerator. And denominator, x plus 1 over x plus 2 and minus 1 here. So again, we're going to multiply top and bottom by x plus 2. And this will give you x plus 2 is not equal to 0. You can only do this multiplication by a non-zero number. So after cancellation, you will have x plus 1. This is numerator. You cancel the denominator from the numerator. And here it becomes x plus 1 minus 1 times it. Don't forget the parentheses. All right? So if you simplify it, so it's x plus 1 minus x minus 2. X cancel. 1 minus 2 is negative. So it's negative x plus 1. And here there's no restriction, no like bad point. So the domain is a set of all real numbers except x, except the point negative 2. Except the point negative. So this is a domain. All right, so that's a second problem. Now let's see the third problem. Third problem, we are looking for the inverse function of a function fx equal to cube root of x minus 3 and plus 3. So to find the inverse function, first we're going to name fx by y. So there are two ways. You can, at this step, you can exchange x and y and solve for y, or you can do that exchange in the final step. Whatever way, it doesn't matter which one you do this exchange. You can do this exchange right now. So we exchange. This step is crucial for you to find the inverse function. Exchange x and y. Exchange x and y. You have x is cube root of y minus 3 plus 3. This cube root only covers y minus 3. It does not cover plus 3. Check that. And then you're looking for y in terms of x. So we're going to move 3 to the left side. And we take cube, the third power. We take third power because we want to cancel this cube root. And then we can move negative 3 to the other side. So if you want a better looking, you can write this way. You don't have to expand it. Many of you expand it. It's okay because it's just cubed, so, but still it will take several minutes to get the correct answer. But you don't have to expand it. This is good enough as a final answer. All right, this is good enough as a final answer. Problem 4, we have a function determined by the pairs 7, 9, negative 1, 0, and 2, 6. This is a function. It means when you have input 7, output 9, input negative 1, output 0, input 2, output 6. Then we're looking for F inverse. F inverse means you just exchange 7 and 9, exchange negative 1 and 0, and exchange 2 and 6. This is a inverse function. And then what is F7? F of 7 is 9. F inverse of 9, F inverse of 9 is 7. And it's very strange. Many of you put undefined. I don't know how you get that undefined. This is defined. F inverse of 6 is 2. F2 is 6. If this 6 is outside of the domain, if you have some number not equal to 9, 0, and 6, you can write undefined or does not exist. But this 6 is here. It's not like other problems. All right, so this is a 6. Problem 4, you get 6. Problem 5, we're looking for the vertex under the symmetric axis for the function, quadratic function f(x) equal to negative 2x squared plus 5x and minus 3. You can have two ways to solve it. One way, you find symmetric axis, x equal to negative b over 2a. This is the formula. Symmetric axis is negative b over 2a. So negative b is a 5. 2 a is negative 2. So it's a 5 over 4. So the symmetric axis is x equal to 5 over 4. The number 5 over 4 is not a symmetric axis. This is a symmetric axis. It's a line. And what is a vertex? Vertex is negative b over 2a, exactly this number, and f of negative b over 2a. Okay, so you get 5 over 4, and you evaluate the function at 5 over 4. Just do the evaluation. It is a 5 over 4, comma 1 over 8. This is number 8, not infinity. 1 over 8. Okay, so this is vertex, symmetric axis. Number 6, well, we are trying to form a polynomial function with zeros and degrees. We have 0, negative 2, multiplicity 2. So fx can be x minus negative 2. You see, many of you forgot this parenthesis. This is half of parenthesis. X minus negative 3. Yeah, multiplicity 3, and together the sum is 5. So that's it. So don't forget this parenthesis. Pair them. Okay. Okay, so 7. Problem 7, we have a rational function. Fx is equal to 2x squared minus 3x and plus 5 over 3x squared plus 2. We're looking for the asymptotes. We have vertical, horizontal, oblique. Well, this one, to find the vertical asymptote, you check 3x squared plus 2 equal to 0. You're looking for the candidates. This does not automatically give us the vertical asymptote, but it will give us the candidate. And this will imply x squared equal to negative 2/3. No solution. No solution, no vertical asymptotes. No solution, no vertical asymptote. If it has solution, you must verify if the numerator is also 0 at that point. Again, the solution does not automatically give us vertical asymptote, but if there's no solution, definitely there's no vertical asymptote. Oblique asymptote. Oblique asymptote happens if the degree of the numerator is equal to the degree of the denominator plus 1. So here, the degree of the numerator is equal to the degree of the denominator. So no oblique asymptote, no slant asymptote. Okay? Then horizontal asymptote. Horizontal asymptote, we check that if the degree of the numerator is equal to the degree of the denominator, definitely it will have the horizontal asymptote. So the idea, many of you showed me the idea, it's very good. So we just divide the top and bottom by the highest power. So we divide the top and bottom by x squared. Numerator and denominator together divided by x squared. We will get 2 minus 3 over x plus 5 over x squared over 3 plus 2 over x squared. When x becomes bigger and bigger, larger and larger, this term disappears, this term disappears, this term disappears. It will converge to 2 over 3 as x approaches plus or minus infinity. So the horizontal asymptote is y is equal to 2 over 3. You see here, x already approaches infinity, so x won't disappear. You only have y equal to, it's a horizontal, y equal to 2 over 3. So this is a unique asymptote. Problem 8. Problem 8 is a mathematical induction. It has its own format. Don't skip any step. Okay, so we prove by mathematical induction. For n equal to 1, it says for all the positive integers, so all the positive integers starts from 1. For n is equal to 1, the left hand side is just 1 cubed is equal to 1. And right hand side is equal to 1 times 1 plus 1 divided by 2 and the quotient squared. 1 times 1 plus 1 is 2. 2 over 2 is 1. Squared is still 1. So you verify. You see here, you separately compute the left hand side and right hand side. You cannot put them as equality because you don't know if they are equal or not before you prove it. So you can only separately compute the left hand side and right hand side. But because you see this is a 1, this is a 1, so we put left hand side is equal to right hand side, the statement is checked. So we only check for the n equal to 1. Now we say assume that the statement is true for some number. Which number? I don't know. We just use a letter k. Okay, and n can be very like flexible, 100, a million, a billion, whatever. But n, we say just for the unknown number k. It's fixed. K is fixed. We assume it's already. We already know the statement. The statement is true for n equal to k. K can be 1. We already verify. Okay. Now for next one, n equal to k plus 1. Assume we have some base point. What's next step? We still start from left hand side and right hand side. Okay, so you see in the statement it says n cubed. N this moment n is k plus 1, so it's k plus 1 cubed. What is the pattern of this sum? This sum just means the first integer cubed, second integer cubed, third 3 cubed, 4 cubed, 5 cubed. So because you have infinite, you don't know how many terms you have, so that's why you put the dots. But we know that the term right before k plus 1 cubed is k cubed, and then you see k plus 1 cubed, right? And 1 cubed plus 2 cubed plus up to k cubed, that's exactly, I think I forgot to write. The statement is correct. Then we have this. The statement is correct. It just means this is correct. Okay, so if you write one more term before this k plus 1 cubed, you will see this is exactly 1 cubed, 2 cubed, 3 cubed, 4 cubed, up to k plus 1, k cubed. But we know that by here, sorry. We should put it here. By our statement, we assume we already know this is correct, so we can simplify this long indeterminate sum. I don't know how many terms, so that's why I say it's indeterminate. To this compact, short, clear expression. Okay, this one, it is k squared, k plus 1 squared, 2 squared is 4. It is k plus 1 cubed. So here you have factor k plus 1 squared. Here you have 3 factor of k plus 1. So I'm going to write, let's write here. So we factor out k plus 1 squared. Then this is a k squared over 4. Here you have a k plus 1. Right? You factor out 2 copies, you have 1 copy survives. And if you simplify it, you will see this is k squared plus 4k plus 4, and then over 4. And this is exactly k plus 1 squared and k plus 2 squared. Check that, it's exactly. Okay, this is the left-hand side. It's equal to this. And in this process, we do use this hypothesis. And now let's see the right-hand side is a k plus 1. This is n. This is n. And n plus 1. So it's k plus 1 plus 1. This is n plus 1. And squared over 2, and then squared. Right? We just follow the right-hand side of the statement. And we simplify this a little bit. So k plus 1 squared. This is k plus 1 plus 1 is k plus 2 squared over 2 squared over 4. So you see right-hand side is also equal to this rational expression. Left-hand side is the same. So we get left-hand side is equal to right-hand side for n equal to k plus 1. First step, we verify the statement for the first possible value. And second step, we assume statement is correct for k, some number we don't know. And third step, we will go one more step. We will go push further. We let n be k plus 1. We separately compute the left-hand side and right-hand side. You can never put them equal because you have not proved it. So then we will say by mathematical induction, the statement is correct. Okay, for all positive integers n. That's it. For all positive integers n. Okay, this is problem 8. Problem 9. We have the quadratic function negative x minus 3 squared minus 4. We want to determine the increasing decreasing interval and the condition over some given interval. And 1, 2, 3, 2, 3, 4. From here, we know the vertex is 3, negative 4. This is a 3. This is negative 4. So remember that fx is equal to a x minus h squared plus k. It has to be minus h and plus k. So the vertex is here. 3, negative 4. This is 1, 2, 3, negative 1, negative 2, negative 3, negative 4. And because the leading coefficient is negative, the opening is downward. Opening is downward. Okay, then we can see on the interval negative infinity to 3, fx is increasing. On 3 to past infinity, fx is decreasing. On the interval, what is the given interval? Negative 10 and negative 2. Where is negative 10, negative 2? Negative 10, negative 2 is here. This place is right, very, very low. So fx is, of course, increasing. Okay, that's it. That's it. Don't get the wrong opening. If you get the wrong openings, you will have the wrong answer. Okay, problem 10, assume we have fx equal to x plus 3 to the fifth power, x plus 2 to fourth power. We're going to determine the zeros, multiplicities, and whether the graph crosses or touches the x-axis at the intercepts, at the zeros. So zeros, here you get a -3 with multiplicity 5 here, and -2 with multiplicity 4. We know that the graph, if the multi will cross the x-axis at -3, because this is odd. Odd, cross, even, touch. Even is touch, okay? So it will cross x-axis at -3 and touch the x-axis at -2, and that's it. Okay. Problem 11. Problem 11, fx is 3 over x squared plus 4. 3 over x squared plus 4. Okay? So this one, first of all, you have to realize x squared plus 4 is never equal to 0. So fx has no vertical asymptote. It has no vertical asymptote. It's not like that x squared minus 4. X squared minus 4 can be 0, but x squared plus 4 cannot be 0. Okay? So the domain is from negative infinity to positive infinity. And it's a symmetric. Fx is an even function. Even function means the graph is symmetric about the y-axis. And the intercepts. So the y-intercept f0, which is 4 over 3. Y-intercept, you let x be 0, y 4 over 3. X-intercept, you solve, you get fx equal to 0. fx is 3 over x squared plus 4. But 3 over x squared plus 4, no solution. So it has no x-intercept. No x-intercept. Okay, what else? Horizontal asymptote. You let x approach infinity, you see the denominator will be greater and greater. So horizontal asymptote is y equal to 0. Is y equal to 0. Right? You let x be infinity, or you just divide the top and bottom by x squared. So you always get 0. It has horizontal asymptote, y equal to 0. It has no oblique asymptote. So if you want to sketch it, so the f0 is a 3 over 4. Anyway, let's just assume this is a 3 over 4. And if you want to make it better, you can let x be 1. X is a 1, so it's a 3 over 5. 3 over 5 is slightly smaller. X over 2 and so on. So make it closer and closer to 0. This is y equal to 0. Y equal to 0 is x-axis. This is the right side and left side. Remember, it's an even function. The graph is symmetric about the y-axis, so it looks like this. We don't need more information. Need more steps to verify it, because we don't have enough tools. Okay, sufficient tools. So you just get this like the bridge. All right. So this is the discussion of a third exam. If you have any questions, you can send me a message or email. Okay, this is the first page. Second page. Page 4. last page. All right, thank you very much.